In this video we're going to be looking at the perpendicular bisector theorem and showing why it is true. Let's begin by building the physical structure upon which the theorem is based. First we draw a chord across the circle, then we draw a line that's perpendicular to the chord. Because the line is perpendicular, we know that the angle between the line and the chord is 90 degrees. The chord splits the line in two, and now let's look at what the theorem says. The perpendicular bisector of a chord must pass through the circle center. Let's break this statement down so that we can understand what it means. The statement talks about the two structures that we just created. We have the line which is perpendicular and we have the chord in blue. The first part of the statement says the perpendicular bisector of a chord. What is a perpendicular bisector? Well, a bisector divides an object into two equal parts. The perpendicular bisector is a perpendicular line which bisects the chord. So for example, if this is a perpendicular bisector, both sides of the chord would be the same length. That's what we can see here. What the theorem says is that if this is a perpendicular bisector of the chord, it must pass through the circle center. In other words, it cannot be in any other position, and this is what we're going to prove. Now I'm going to do something strange here and draw several other shapes and compare them to the circle. Now these shapes have something in common with the circle. Can you see what that is? They all look quite different from the circle, but there is one property that all of these shapes and the circle share. I'll help you figure that out by adding just one element to each of the shapes. Can you see it now? Yes, all of these shapes are symmetrical. The line going from top to bottom on each shape is called the line of symmetry. The definition of a line of symmetry is an imaginary line that cuts an object into two parts that are mirror images of each other. And if you look at all of these shapes, the right side of the line of these shapes, the line of symmetry, is just a reflection of the left side of the shape. And that's what it means to be symmetrical. But if you look at the circle, it has exactly the same property. If I draw a line through the center, this is the line of symmetry. The right side of the circle is a mirror image of the left side of the circle. And one fact about the line of symmetry is that they always pass through the center of the shape. This line of symmetry that the circle has is going to show us that the perpendicular bisector of a chord must pass through center. So let's see why the line of symmetry helps us. Let's just take a simple shape. Let's use a square. If I draw a line from the line of symmetry to the edge of the shape in one direction, and then I do the same thing in the opposite direction, I draw a line perpendicular to the line of symmetry to the edge of the shape, then these two lines must be exactly the same length, right? Because this side is just a mirror image of the other side. So this is just the same shape in reverse. So the length of the line of symmetry to the edge on both sides must be exactly the same. Now, looking at the circle, let's put the chord back and let's put the right angle back. That shows that the line going through center is perpendicular to the chord. This is the line of symmetry of a circle, and because it's the line of symmetry, the left side of the circle is a mirror image of the right side of the circle. So the right hand side of the chord must be the exact same length as the left hand side of the chord. So the line going through the center that's perpendicular to the chord must be a perpendicular bisector, because the two sides of the chord are identical in length. But here's a question. What would happen if, instead of drawing a line through center that was perpendicular, I drew a line through another part of the circle, perpendicular to the chord? Well, let's try it. Clearly, this line which is perpendicular to the chord doesn't bisect it because the two sides of the chord are not the same length. And I'm going to visibly illustrate why the line that's perpendicular does not pass through the center of the circle. Let's put in the circle center, and now let's move the chord along with the perpendicular line and the angle and see what happens. And there you go, something is completely wrong. The distance from the perpendicular line to the right side edge is not this, it's actually longer than that, and the distance from the perpendicular line to the left side edge is not this. The distance is much shorter, so neither end of the chord is at the circle's edge. We would have to move the chord and the perpendicular to a different position in order for both ends of the chord to be at the circle's edge. Therefore, if the length of the chord on one side of the perpendicular is not the same as the length on the other side, we can see that here, the only way that the two ends of the chord can be at the circle's edge is if the perpendicular line is not passing through center. So a line that is not a perpendicular bisector of a chord does not pass through the circle center. But for a perpendicular bisector of a chord within a circle, the lengths of the chord on either side of the perpendicular are equal. The ends of the chord are at the circle's edge, so the perpendicular bisector of the chord is at an equal distance away from the edges, which means that it must be passing through the circle center. And with that, we've shown why the perpendicular bisector theorem is true. There are other more concise ways to prove this theorem, and in another video I will be showing you another way. But that's it for now. Thanks for watching.